So welcome back to the defects that occur in the welding or the weldment that determine the quality, weld quality. So one of the important defects that occur is the cracks. The cracks can occur at different locations within the weld area, and they are given different names with respect to it. So in this figure we can see mainly the two types, the longitudinal cracks as well as the transverse cracks. The cracks that develop parallel to the weld direction, that is known as the longitudinal cracks, and which occurs perpendicular to the length of the weld, that is known as the transverse crack. And the underbeat cracks that develops in the heat affected zone, as well as the toe cracks that develop across the along the length of the weld in the heat affected zone. There could also be crater cracks that develop randomly at the end of the welds. So these are the main types of the cracks that develop. Now the reasons for the occurring of cracks within the weld area are listed here. Uh, the first one is the temperature gradients that occur during the cooling of molten metal in the weld zone. So due to this temperature gradient, it could rise to the thermal stresses, and these stresses or opposing forces or contracting forces could pull the weld or the cooling metal, and it could result into a crack. Now the second one is the variation or large variations in the composition of the alloy or the weld zone. So we have seen earlier that the weld zone will be consisting of the base metal, the filler metal, the slags, etc. And if this total composition is not uniformly distributed, then there will be local variations in the composition, and this could result in different cooling rates at different locations. So in some parts of the weld zone, the temperature may be higher compared to the other part, and this difference in temperatures or this difference in cooling rate could lead to the thermal stresses again, and finally some cracks may develop. Another reason is the sulfur and hydrogen embrittlement. Now this is the segregation of the sulfur and hydrogen molecules along the grain boundary, which you had studied in the previous semesters. Now due to this hydrogen and sulfur embrittlement, the weld zone will be losing its ductility. That is, it becomes more brittle, or it resists the deformation changes. That is, due to the loss of ductility, it the cracks develop easily under a load compared to the original nature, that is before the embrittlement. So the cracks could develop either one or combination of these reasons. Now the cracks are also differentiated on the basis of when they were formed. The hot cracks are called so as they were developed or they occurred when the total weld zone were at elevated temperatures, and in case of cold cracks they are developed after the solidification of the weld pool. Now some of the methods to follow to reduce the formation of cracks within a weld zone are: the first one is to modify the joint design to minimize the stresses developed during shrinkage. Now due to the design of the joint area or the weld area, the molten metal may be constrained or restricted to not properly contract or shrink during the cooling. That is, they may not be able to shrink properly while cooling, and this could result in the formation of stresses. So if you are modifying the joint design so that the proper cooling takes place, then these stresses could be avoided and the cracks could be avoided. The second one is to control the parameters, the procedure followed, or the sequence of the welding operation followed, etc. So these all influence the heat input as well as the temperature gradient developed in the weld zone, which could, if not followed properly, result in the formation of cracks. Hence, controlling these parameters, procedures, and the sequence, we can control the number of voids or number of cracks formed within the weld zone. Now, preheating the components. The third one is to preheat the components so as there is so that we can control the cooling rates. So once the weld metal or the base metal is preheated before welding, there is less temperature difference between the molten metal as well as the base metal, and as a result the cooling rates can be controlled and there is less thermal stress developed. So consequently the cracks developed will be less. And the final one is to avoid the rapid cooling of weld pool. So rapid cooling means the cooling rates are higher again, and this could lead to the more number of cracks developed. So by controlling the cooling rates or by avoiding the rapid cooling of the weld pool, by making the loss of heat or dissipation of heat from the weld pool slower, we can control the number of cracks formed. So these are some of the methods that could be followed to reduce the number of cracks and improve the weld quality. Now the next defect is the lamellar tears. Now these occurs in the welding of structures that were formed by plastic deformation methods such as the rolling. Now even though these structures or the rolled components are said to be anisotropic, that is their properties don't change with respect to the direction, it is found that they are weaker in the thickness direction. When testing in the thickness direction, they are found to be weaker. For example, in this figure we can see two rolled components that are welded, and while tested in the thickness direction, or we can see by depicted by these black arrows, a tensile force is applied across the across their thickness, and as a result a crack is developed, and these are known as a crack like defect is developed, and these are known as the lamellar tears. Now this is due to the presence or alignment of non-metallic impurities as well as the inclusions during the plastic deformation of the base components. Due to the presence of these non-metallic inclusions during the melting or during the cooling of the molten melt, the shrinkage occurs and it causes the lamellar tears. Now to avoid these lamellar tears, we can redesign the joint and accommodate for the shrinkage of these inclusions that were formed during the plastic deformation of the base component.